Good evening. Today I will be discussing Lab 4, Macroscopic View of DC and RC Circuits. The purpose of this lab is to observe the differences in interaction when resistors in a circuit are placed parallel to each other, as in the rightmost image, versus in series, as seen in the left image. Our observations will correspond to three important principles: the loop rule, the principle of current conservation, and Ohm's law. The loop rule states that for a closed loop, the sum of the potential or voltage differences across the energy source and resistors will be zero. This law is equivalent to the law of conservation of energy, as voltage is not being created nor destroyed. Secondly, the principle of current conservation will be practiced in that at each node, or branch within a circuit loop, the total current flowing into the node will equal the total current flowing out of it, since charge is conserved for systems in steady state. Lastly, we will use Ohm's law to measure the current at any location in the circuit, which will be equivalent to the change in voltage divided by the resistance. In the first part of the lab, we were asked to predict the ammeter readings for a simple circuit consisting of two 1.5-volt batteries and two resistors, one with a resistance of 47 ohms and the other with a resistance of 100 ohms. I used Ohm's law to predict the current. Note that since the resistors are in series with each other, the current at locations 1 and 2 is the same since there are no breaks in the circuit. Thus, I is equal to the change in voltage, 3 volts, divided by the net resistance, 147 ohms. I is thus equal to 0.0204 amps. My prediction was correct, as the ammeter output a current reading of 0.02 amps at locations 1 and 2. Note that when the orientation of the ammeter was reversed, the same current of 0.02 amps was measured. We were then instructed to replace one of the two ammeters with a voltmeter. At this point, the voltmeter read 3 volts, since the voltmeter wires have no internal resistance. Thus, the voltmeter is able to detect the change in voltage between sites A and B. The ammeter detects a current reading of 0 amps since the circuit has been broken and therefore no current flows past location 2. Next, we measure the potential difference between different sites, labeled A through H, in a series circuit. Note that when you are trying to determine the potential difference between two locations, it matters where you place the red and black wires. To obtain the correct sign for the change in potential difference, the black wire should be placed at the first site and the red wire should be connected to the second site when going clockwise around the loop, as shown in the image on the right. According to the loop rule, the sum of the potential differences across the loop should be 0. Our results support this prediction, as the net potential difference for the round trip was 0 volts. Note that even when the voltmeter is attached, the current is the same as when we had two ammeters connected, since the current is at steady state with no breaks. Here is a plot of potential versus position for the circuit. The negatively sloped regions represent the change of potential occurring at each of the resistors. The greatest drop in voltage occurs across the 100 ohm resistor, since the resistance was at a max at this location. As mentioned earlier, the voltmeter reading across the 100 ohm resistor was 0.02 amps for the circuit in which the ammeter was in series with the resistor. However, a different result is obtained when we place the ammeter and 100 ohm resistor in parallel. The ammeter has the effect of decreasing the total resistance, leading to an increase in current since current wants to flow to the branch with the least resistance. For the ammeter in parallel, the current is measured to be 0.06 amps. We can calculate the resistance of each of the circuit elements from the data we obtained when the ammeter was in series with the resistors using Ohm's law. As a reminder, resistance is the absolute value of the change in voltage divided by the current. To determine the resistance of each element, the change of voltage for that location was divided by the current value of 0.02 amps. There is no resistance over the wire or ammeter regions. We were then asked to investigate RC circuits. When a 10 ohm bulb and capacitor were connected in series with a 9 volt battery, the light bulb initially was very bright but faded very quickly. Also, since the battery is present, it is able to charge the capacitor. When the battery is removed and the capacitor is connected directly to the bulb starts out very bright and slowly dims and the current approaches 0 amps. To determine the time it took for the capacitor to fully charge the 10 ohm bulb, the voltmeter was attached to the ends of the capacitor. The results are shown for the time it took to charge and discharge the capacitor. The process was then repeated with the 20-ohm bulb. As expected, it took significantly longer to charge the bulb with the higher resistance. In the last section of the lab, we were asked to determine RC, the time constant value for a circuit with a 30-ohm light bulb. RC was found by plotting the natural log of the change in voltage across the capacitor divided by delta V naught, the initial voltage difference across the capacitor, versus time. The slope of this graph is equivalent to the negative inverse of RC. The value for RC from the slope was calculated to be 6 seconds. The expected RC value is computed as the product of the resistance and current and is also found to be 6 seconds. Thus, the percent difference between the two values is 0%. If we did this experiment in real life, the current values obtained would have been lower than the observed values. This is because the ammeters we used in the lab were ideal ammeters. Real ammeters have resistance. Finally, if we used a battery and capacitor with no resistor, we would expect an increase in the time it takes to fully charge up the capacitor. This is because the circuit components would no longer behave as ideal elements and would therefore contain some internal resistance as current passes through. Thank you.